Hello, thank you for your patience. And now a small announcement: if you are here for the compiler talk, then you are wrong and we are right, because it will be a mobile graphics talk, actually. So we have Aras here, Aras Pranskavicius. He is our rendering architect at Unity. And yes, he is. So, and we will talk today about the GPU, optimizations, stuff like that. We'll cover a little bit what's the difference if you are coming from the desktop and you want to optimize your graphics for the mobile devices. And we will generally cover how to optimize on the mobile devices. So, okay, so let's start with the common knowledge. Probably everybody knows that already, but on the mobile devices, usually the opaque geometry is the best one you can get. And you should try to avoid alpha testing if you can. And you should reduce your alpha blended geometry as well. And here's the order, which is best. And usually Unity takes care of that. So you don't usually need to do anything about that. And the last thing is the post-processing is super expensive, quite expensive on the mobile devices, and we will take you through the why it is so and why you need to take care of it. So the thing you notice about the mobile devices is that the performance difference is quite widely ranging, approximately 10 times from the low-end mobile GPUs, like on the iPhone 1, for example, and up to iPad 2. And your weapons, how to optimize, how to scale with the different hardware is, of course, you can do different resolutions. You can force a lower resolution rendering. You can render to render target and upscale. You can use the Android, you can upscale automatically. You should try to reduce amount of the post-processing, especially if you are porting your game from the desktop. Then the first thing you should try cutting is post-processing. Then the next thing, you can up on the iPad 2, for instance, you can waste a little bit of your GPU time by using anti-aliasing. And on a lower end hardware, you would not do that. Anisotropy is very good leverage. You can anisotropy gives you a very crisp look on your textures, and you can crank it up on Tegra 3, coming Tegra 3, on the iPad 2, and you would reduce it on the lower end devices. Shaders is a good way to balance your load. By Unity allows you to have a fallbacks have a simpler shaders. Okay, and just a little bit of our insight, that CPUs on the mobile devices, it's a little bit strange. Usually on the desktops, you think about the GPU as being really fast, and you want to put as much work there as possible, move all your code to GPU. On the mobiles, the balance is a little bit different. We see that there is more and more powerful CPUs coming on, and with many cores. So what we are looking ourselves in the future, that we are going to put more work actually on the CPUs. For instance, on the multi-core devices like iPad 2 have 2 cores, Tegra 3 has 4 cores, and we will see more 4-core devices coming on in the future. So right now we are already doing skinning and batching particle calculation on the multi-cores, and it is quite easy for us to do. And we do some, in the Shadowgun we had some physics as well running in parallel. And it is something we're gonna improve as well in the future. And we want to have occlusion culling and post-process, maybe moving post-process effects, calculating with shadow maps, doing more physics on those CPUs in parallel, and actually moving quite some work from the GPU onto the CPU, or using CPU to reduce substantially the work on the GPU side. So that was an introduction, and let's cover a little bit about the mobile GPU architectures. So right now we more or less have 4 different approaches on the mobile GPUs. Some of them are kind of similar, and some are kind of different. For instance, Tegra and Imagination Tech Power VR SGX, they are quite different. And all those architectures are more or less substantially different from what you can find on the desktops. And I think it's crucial to understand how these GPU architectures are working. If you want to optimize, you need to understand why certain things are this way. And once you understand, you know where to find for bottlenecks. And when we look at the mobile GPUs, usually it's a very smart hardware. I would say it's somewhat smarter than the desktop machines. Why? Because there is a very low memory bandwidth available for those devices, and there is not that many. The thermal, you cannot really. You need to have your phone without the fan, and you need to have it in the hand, so it can't be really warm, kind of. So there's a lot of constraints coming on those mobile devices. So the guys who are making GPUs, they know that, and they try to make their hardware as smart as possible and use as less thermal and less memory bandwidth as possible. So most of those solutions in the mobile GPUs are specifically to overcome those limitations. So, and we more or less can separate those GPU types into these three groups. The PowerVR is tile-deferred. Adreno and Mali. Adreno is a Qualcomm device, and Mali is a GPU from ARM, quite new one. They are somewhere in the middle between tile-deferred and classic, so that's called classic. And the Tegra classic is something what you would usually see on a desktop device. It has some modifications, but generally the architecture there is coming from the desktops. And one of the most important things about the mobile GPUs is how they treat the overdraw. Most of them are geared really well towards reducing the overdraw. Why? Because overdraw is usually, when you have a lot of stuff, a lot of overdraw, it can kill your memory bandwidth really easy. So, of course, mobiles, the people who are working on those GPUs, they think hard how to overcome that problem. So, and here I have two types of deferred, two types of the solutions for reducing the overdraw inside GPU. One is deferred, and that's what PowerVR, what Qualcomm and what ARM are using. It's called deferred tiled or deferred rendering, and usually what it does, it will split when you have a frame buffer, it will split the frame buffer into small tiles. Those tiles are pretty small, like 16 by 16 pixels. Can vary on the hardware. And when the frame is being rendered, it's actually, the GPU will bin those polygons. When you submit all the geometry of the scene, it will go and assign those polygons to those small tiles. And then it will, instead of rendering everything in one go, so it will assign those polygons into small tiles, and then it will go tile by tile rendering. And what it gives us very good locality, and it's always banging on the same small piece of memory, so you can say that memory piece can be basically in the cache, very close to, on the GPU, very close to arithmetical units. So you save you don't need to write this into the memory. You don't need to use bus, memory bus. So everything stays on chip. That's why it's very fast. And while on this small tile, it can use small micro Z buffer or some other ways to figure out that, okay, I don't need to render those polygons because they will be occluded by others. Because GPU is working on a complete scene. It knows in this tile, these guys are covering, yes, they are covering other polygons. So GPU will go and just reject those ones, and it will render only front one. That's how works. That's how SGX, Mali, and Qualcomm device operate. If you look at the Tegra, it does it a little bit differently. Instead, there is it renders everything in the same order as you would submit geometry, like normally, like on the desktop it would do. It just has this smaller resolution Z buffer, which allows them to call on 2x2 so-called quads. So the one essential thing there is because it does not bin geometry, because it doesn't process the scene, it renders it in the same order as you would submit geometry. It's very important to sort it correctly. So the first things which are rendered, they are very good occluders for things which are coming afterwards. It is something what Unity is doing automatically nowadays, especially in case of the Tegra, but I will show you later on how you can help it in certain cases to get even better performance. And here is a comparison between Tegra 2 and iPad 2 and how well they reject, what is the performance of rejecting the invisible stuff on screen. So if you look at as I said, the Tegra can reject only on 2x2 pixels, while iPad 2 can reject at 32 pixels, so it can reject quite much more pixels at the same time. And you can see the difference in timing. It's pretty substantial difference at the rejection rate. So basically the idea here is that on an iPad 2 you could render actually quite more complex scene in sense of the overdraw. And here you can see more or less a graph comparison. You can see on the x-axis we have a, what do we have? So on the x-axis we have amount of overdraw, and y-axis it's time basically. So we had to see the difference between Tegra and iPad. And here you see that both scales linearly with the amount of overdraw, the graphs are a little bit different. So basic insight that it's very important for Tegra to sort correctly, because if you improve the sorting, you can get that red curve down. On iPad, it doesn't really matter. This curve will always be the same because the GPU is smart enough to figure it out. On the Tegra, you need to help it to lower that red curve. And the only thing you can help is how you sort objects. And there's something we have already in Unity. And there is another thing which is, I hope will be coming soon, is occlusion culling can help that. We can spend quite a lot of CPU cycles. On Tegra, we have very powerful CPUs, much more powerful, I would say, than the GPU also. So you can spend quite a lot of CPU cycles on rejecting those objects which are not visible on the CPU side before we send it even to GPU. Okay, so what this architecture differences in architectures gives us, for instance, we can tile and tile deferred. They can save you quite a lot of the frame buffer writes. Classical architecture can't really help you with reducing the frame buffer writes. So in the classical architecture, you need to write quite a lot of it to the memory. GPU will write quite a lot of it into the memory. And another good thing is that because of the rejection, you can save quite a lot of the ALU instructions on the deferred architectures. Yeah. It goes back and forth, but the only interesting thing here is that SGX is quite smart about prefetching textures. So in many cases, it can prefetch the texture itself, the values, before even it comes into the pixel shader. So for instance, when you look at the cycles, you can see a pretty complex shader. When you look at the cycles on the SGX hardware, you can see a pretty complex shader, like take one texture, multiply with another texture, and store that, and like output that result. And you can see that it takes only one cycle. And that was very surprising for me the first time I've seen, because, well, how can you do in one cycle, sample 2 textures and multiply them together? It's impossible. It turns out it's possible because SGX will prefetch both texture reads before it even gets into the fragment shader. How it does it, in order to do it, it needs to know, it kind of knows that that the text coordinates must be always in the XY component of your interpolator. So the hardware knows, like, okay, I have to fetch those 2 textures here in this fragment shader. It knows it up front. There's a TSP module which does that actually. And at that point it says, okay, I will have to fetch them. And I know that I'm fetching it from those 2 interpolators. And if there is no modifications on those XY coordinates, it will do that before it enters the fragment shader. So that's very important to know when you're writing shader, that you shouldn't pack more than one. You shouldn't put more. Usually on the desktops, you would pack 2 texture coordinates into the same into the same interpolant. You should never do that on the SGX hardware, because then you will get only one of them will be prefetched. So, and again, as I mentioned, the small tiles help you to get a better cache coherence. So you can get more better anisotropic filtering, because it usually reads a little bit around. You are not really bound by MIP maps. You can actually, in some cases, even skip MIP and not use MIP maps, and the tiled architecture can give you pretty good results. But you need to be really careful on the classical architecture. You need to always have MIP maps, and you need to be careful with the amount of anisotropy you're using. Another thing good about the tiled architecture that you can get a quite high Z precision, because it's a very small buffer, and it can do some tricks. It can render in 32 bits, even if you say that your frame buffer is 16-bit, and it will, while writing that tile into the memory, it will convert from 32-bit to 16-bit. And basically, it's internally you have much higher precision, and when you store, you have it's only one conversion to 16-bit. Okay, so let's take a look at couple of cases how it actually performs in the real life. For instance, there's 2 games here which we were profiling or helping developers to work on. And there's a Shadow Gun in one of them, and there's a Blade Slinger. It should be announced today. So the Shadow Gun was released like yesterday, and Blade Slinger is not yet released. It will take some time before they release the game, but it's already announced. So here, I took those 2 games as an example, and let's take a look. For instance, on the iPad 2, 4x MSA anti-aliasing in case of the Blade Slinger, it's 6 milliseconds per frame, and in case of the Shadow Gun, it's only 1 millisecond per frame. So it's pretty impressive for such a big resolutions. It's an iPad 2 resolution, and it takes only 1 millisecond to do anti-aliasing. So the tiled architecture is very good for doing anti-aliasing. The question why it's 6 milliseconds in the Blade Slinger, it's because we're using post-processing, and there are some tricks there, and the scene itself is more complicated. There is more vertices, more polygons to render, and having more edges of the polygons makes MSA a little bit more slower, actually. So it's still not free, but very impressive. I mean, you can get almost for free anti-aliasing on the iPad 2 hardware and on the Mali hardware. Another thing is anisotropic filtering. So in both Blade Slinger and Shadow Gun, just cranking up anisotropy, using the maximum anisotropy on all textures, takes only 3 milliseconds on both on iPad 2. And I mean, it gives a very crisp look for 10% of your frame. Tegra supports as well anisotropy, but it can be, you need to be careful a little bit. One of the reasons is because it's a different architecture and because the anisotropy can be better on the quality can be better, but it will cost you a little bit more. Usually, we would say we always use MIP maps. And we believed ourselves in that until we actually started profiling. And it seems that on the SGX, again, on the tiled hardware, it doesn't really matter that much. Well, it burns like using no MIP maps. For instance, in case of the Bladeslinger and in case of the Shadowgun, we tried to disable the MIP maps completely. Just with no MIP maps. And it's a huge textures. In case of Bladeslinger, it's 2,000 by 2,000. And it would only cost us 10%. So it's very surprising. Doing the same on Tegra would kill you completely. So on Tegra, you need to make sure that you have MIP maps. So the reason why sometimes you want to reduce to turn off MIP maps is because you want to. Artists would say, "Oh, the MIP maps, they are blurry, so let's turn them off because then we will have a crisper look." So while it gives you a crisper look, it gives you much more aliasing. So instead of doing that, it's actually much better to use anisotropy, to use MIP maps and use anisotropy. It will cost you the same amount, and it will work well both on iPad 2 and on Tegra. So prefer anisotropy than doing anything with MIP maps. There's one more. So tile deferred, though it sounds a little bit like I'm saying, oh, it's so great comparing with the classical architecture. Well, there are some downsides there as well. So one of course, because it's more smarter hardware, they need to spend, you can say they need to spend more transistors on that smartness. So we have less stuff for the raw power. And there's one thing which, because there are some internal buffers, but they need to gather all the scene before they can render it, before they can start tiling it. So it needs to be stored somewhere in the memory, and obviously that memory is not infinite. So you can get this scene splits when you're running out of that internal memory. The GPU will have to stall, will have to render everything, and will have to resolve everything, all the frame to memory, and then start, and then continue with the another part of the frame. And we actually run into this in the Bladeslinger around 100,000 vertices per frame. We started to get scene splits. It was in case of the Bladeslinger, it was not crucial. Like the performance-wise, it was not terribly bad, but just reducing the vertex count a little bit by 10%, we get rid of the scene splits and got much faster. And another thing about the tile deferred is very hard to actually measure GPU draw costs. It's much easier on to profile on Tegra or Adreno than on SGX, unfortunately. Do you want to talk?
Go on.
Yeah.
Go on.
You're feeling well? It's a little bit covering the same talk, same material which we had in the talk with the Shadowgun, so I will be a little bit faster here. So one of basically the challenge on the Shadowgun was to optimize for Tegra 2. We wanted to get it in 30 frames per second, and basically most of the work there is done, the optimization side was done on the artwork side, so it's very good to optimize artwork instead of optimizing the code. And they did a very good job on having a low, not that many vertices per frame, and there was, from the start up, we knew that we don't want the full screen effects, and instead we were doing various tricks with the alpha blended geometry, small, where you can contract it when you come closer, so we can control that much better, and you can put the alpha blended, like the light shafts and fog planes, only where you need it. You don't cover the full screen, so that helped a lot. We had no alpha tested geometry at all in the Shadowgun. And the perf hood, with the Tegra, you can get a perf hood profiling thingy from NVIDIA, and it's really great if you want to profile. It's basically the thing to profile your stuff. And I would just cover one thing is that I said about the ordering stuff, but in a shadow gun, we did a trick that because in the case of Tegra, we knew that the character is always in front of the screen, so it always will, and it's kind of big, so it will always cover at least some portion of the screen. So we would use a Unity render queue to always render it in front of everything. So first of all, we would render the character, and then because we knew that the enemies, the shader there is quite expensive, so they're usually sitting behind the cover. So we would force them, using the render queue as well, to render after all geometry. So that would help Tegra to reduce the overdraw. And always rendering skybox last. That is automatic in Unity, but what you can do as well, and what is done in case of the shadow gun, if you know that you are not rendering skybox, and just kill it together, just with some simple script. And all of those optimizations gave us around 15 milliseconds per frame. So we went from 20 frames per second to 30 frames per second on Tegra 2. Another optimization was how the lighting is calculated on the characters, and we got it pretty tight. It's 10 cycles per pixel lighting with light probes on top of that, and and it's quite a flexible approach, and the reason for that is because we did most of the lighting using the single lookup texture. And you can see that the editor extensions which were written to generate those textures. And you can find more details on another talk about the shadow gun. And I think we soon will have them on the asset store, both shader and the generation. And here it just explains that, we had this math, and instead of that math, we just offload everything to that texture, we calculate that offline, and at the runtime, we just use the texture single texture sampling. And we can do quite a lot of interesting stuff with that texture. And in comparison, it runs on the iPad 2, 60 frames.
Is that me?
Yes, that's you.
Yeah, so I'm going to talk about the tools which you can use for trying to optimize and profile the graphics side. So like today we announced that we are doing GPU profiling in Unity 3.5, but like right now it only works on Mac and Windows. And on some of these platforms like iOS, it's just not possible to actually tell which object took how many milliseconds took to render each object due to the nature of the GPU architecture. So some of those GPU profiling tools are not coming in Unity 3.5 yet. So you're basically left with using some external tools. So for iOS, there's sort of the iPhone profiler that's in the app controller part of the build project, and that can tell you by enabling one define in the Objective-C code, that can tell you the GPU time for the whole scene, which is much less information than for each object, but still a good indicator. Apple's tools can tell you how busy the GPU is in terms of percentage. So like if it tells you that the fragment unit is 100% busy, then you pretty much know that the bottleneck is in the pixel shaders, versus if what they call a tiler unit is 100% busy, then probably you use too many vertices or too complex vertex shaders. Additionally, PowerVR on the developer website, we have this unpronounceable shader analyzer, which is basically a shader editor where you can paste GLSL code in, and then it tells you how many cycles would that take. But that's very approximate because that tool does not have the GPU profile for the GPU that's in iPad 2. So it kind of tells you the numbers for a different GPU, which sometimes is close, sometimes it's not. So yeah, that tool looks like that. So if you take any Unity shader, those are usually written in HLSL, or also known as CG. But this tool expects GLSL shader. So if in Unity, you can open compiled shader in the inspector and find the GLSL shader in there and just paste that in. On Android and Tegra devices, like Ronaldo said, there's a really excellent NVIDIA tool which gives you anything you might want, like GPU times for each draw call and cycles for each shader, and it can force like very small textures to see whether your texture resolution bound. And it runs on not only on Windows, which is very pleasing for us who like to use Macs. So yeah, that's very useful. And yeah, it has like nice UIs and stuff. However, one downside is it needs an NVIDIA development board, which you can get from NVIDIA by, I don't know, by registering or something, and they send you this piece of hardware. But it's possible to run this on like real actual phones, but it's very easy to brick them by doing something wrong. On Qualcomm devices, again Android and the Qualcomm GPU, there's Adreno Profiler, which you can get from Qualcomm website. It's also a really nice tool, but it's Windows only. However, what it does well is it works on any Qualcomm device out there. So you can take like Xperia Play and just use that tool on that. And yeah, you can like capture frame and see like which object took what amount of time and debug the shaders even. So yeah, so that's for the external tools. Now for the actual shader performance optimization. So shaders on most mobile platforms we care about are running in OpenGL ES 2.0, except the PlayStation Vita and 3DS and the Windows Phone. So all of them use GLSL shading language, which is kind of like HLSL, but a bit different. So what it does here, which is different from desktops, it has like precision for different types. So whereas on the desktop, you mostly use like float, which is like floating point number. And you might remember if you were doing graphics in like 2002, there was like GeForce FX GPUs, and they had like types in CG language for like half precision and very low fixed point precision. So that's basically the same as GLSL is doing right now for mobile, which is like high precision, which is like most often 24, 32-bit floating point, medium precision, which is most often 16-bit floating point, and low precision is like fixed point, 8-bit number. In Unity, you mostly write shaders in HLSL, and we prefer people to do that because that works on all platforms. So if you write a shader in HLSL, it works on Windows, on Mac, on all the consoles and all the mobiles, and it works on Flash as well, or it will. And for the mobiles, we actually take that HLSL shader and we just convert that into GLSL for mobiles. And you can also write in GLSL directly, but then you're limited to like OpenGL-like platforms, which is like Mac and mobiles. So the general intuition of how to optimize shaders is very sometimes not intuitive. So I'm going to give like some sort of rules of thumb, but then I sometimes find myself that like these rules of thumb sometimes do not apply. So it's very important to actually measure whether your changes to like, oh, I optimized the shader, it looks much shorter now, but then it actually runs slower or something. Yeah, and some of the platforms like iOS does not have any shader profilers whatsoever, so it needs a lot of iterations to try to optimize that. So one thing is to use appropriate precision for all your computations in the shader. So like fixed precision or like low P in GLSL is like that's good for general colors. The range of numbers is like -2 to +2 and like 8 bits. So when you read something from a texture, it's a good thing to put that into like low precision thingy. That's also good for some normalized vectors, but on some GPUs, it's bad if you want to do like swizzles on those values, because then swizzles aren't free. The medium precision is good for most of other stuff which does not need higher precision. And then finally, the sort of the highest precision is for things that really need large numbers, like world space coordinates and some really large possible UV values. So one thing to watch out is to try to minimize conversions between, like, if you read something into low precision variable and then assign that to medium precision variable, that might be not a free thing to convert on the GPU. And some of the GPUs, back when we wrote this talk, we tried profiling different shaders on like Qualcomm devices, and we found out that it pretty much ignores all the precision. And later on, we talked with Qualcomm guys, and they confirmed that like the Qualcomm device internally uses one precision for everything. So that particular GPU doesn't matter. In terms of passing data between vertex and pixel shaders, it's called like varyings in GLSL or interpolants in Direct3D. Most of intuition from desktops or consoles is that you should use as little varyings as possible. But that isn't true for PowerVR devices, which are on all iOS platforms. So on PowerVR, it's much better to use more interpolants if that helps to avoid like dependent texture reads. So if we look at shaders of various levels of complexity, starting from the simplest possible one that just kind of output red shader, to like going to like sample a texture, multiply with the color, do a like diffuse normal map, something. So if we go through these shaders and we draw a sort of plane over the whole screen, and we measure how much time does it take on the GPU. So like simplest possible shader ever that like takes 1.4 milliseconds on iPad 2 to fill the whole screen, and like takes like 14 milliseconds it would take 14 milliseconds on iPhone 3GS to fill the equivalent of iPad 2 resolution. So like you could say like iPad 2 is probably the fastest GPU, followed by Xperia Play, followed by Tegra 2, and followed by iPhone 3GS. To something like per pixelit bump map specular shader, again, the ordering of GPUs is kind of similar, but from that factor alone, you could say like iPad 2 probably 2 to 3 times faster than Tegra 2, for example, GPU. And well, this is probably too complex graph to actually show anything, but it basically shows that the more complex shader gets, it's probably slower no matter on which GPU you run it on. So if you make shader faster, very often it will be faster on a different GPU, but then not always. So yeah, I pretty much said that. And yeah, now back to Ronaldo's.
So let's take a look at optimization specifically for Blade Slinger, which were done on the iPad 2. And when we got hands-on let's say the project, it was running 18 FPS, and it was completely GPU bound. And it's kind of hard to profile on the iPhone, as I said. So we had to do quite a lot of just trying again, changing shader, trying again, changing shader. That's basically how it works. You just change shaders and you measure GPU time. Yeah, that's it. And so after optimizations, it was running 37 frames per second. So it went from 18 frames per second to 37. And actually, then afterwards, we could add more stuff like more stuff, and we'll cover that later. And so the complexity of the scene is 90,000 vertices per scene. It has quite a lot of particles. You can see that, like fire,
and more fire.
And more fire, particles, and more particles. So quite a lot of particles. There's quite a complex shaders on on the walls. I will show later on. Because they can burn, there were two post-process effects: bloom and heat shimmer. Bloom is basically, you know what is bloom, and heat shimmer is the wobbly screen where the heat is. And afterwards, we could get, once we had, after optimizations, we could get it running almost 30 frames per second with 4x MHz-AA and anisotropy.
Was this iPad 2? Or?
Yes, that's iPad 2. So let's look at the tools which we can use for profiling. So although we can't really profile the draw call by draw call, but we can use the Xcode instruments to more or less know where the bottleneck is. And once you launch it, you can get both these for me at least, most important numbers from the Xcode instruments. And so device, that means actually GPU. So it shows you how much time GPU, how during the frame, how much work is done on the GPU side. If you have a device 99% or 100%, that means that you are completely GPU bound. That it's the blocker. If it's lower than 100%, that means that you are blocked by the CPU, and the GPU is taking only, let's say, if you have 30% in this device, then it means that you are comparatively your CPU, you 1/3 of the CPU time on the GPU, because they are running in parallel, of course. But this device percentage, it says you the balance between the CPU and GPU. So the two next things, once you know that you are GPU bound, and it was obvious that in the BladeSlinger we were completely GPU bound. So the next thing I'm looking is tiler and the rasterizer. So the tiler, it means the vertex shader. So why it's called tiler? Because at that point it has to process the vertices and put them and assign them to different tiles. So that's why they call it tiler. But it's actually, for you, it's vertex processing, amount of the vertex process. And the rasterizer, it's how much time the pixel shader are taking. So in our case, in the BladeSlinger case, we were highly rasterizer bound. The tiler, the vertex processing was not that bad. And then there is another interesting thing is, as I mentioned, the split count is how many times the scene has to be stopped and then flushed kind of and rendered, continue to render. And that depends on the amount of vertices you are sending. And the split count in the Xcode instruments, it's not per frame, it's per second. So if you see something except 0, that means bad. You have too many vertices. You just need to scale amount of vertices down. And then I'm using the built-in thingy in Unity where I can see how much time the GPU is taking. You can enable that define in the app controller or now in the iPhone profiler.mm file. So you just enable the GPU time and it will tell you the actual. So after I know that it's GPU bound and I more or less know it's pixel bound, then I'm enabling this counter inside Unity, and which tells me how many milliseconds GPU is taking, and then afterwards I'm starting to experiment with the shaders and see how the numbers are changing. And of course, the first thing you would notice, easy, I just create several buttons, assign press the button and it disables the post-processing. And I press another button on screen and it disables the particles. Press another button and it does something else. It changes the shader. So I'm using these buttons on screen to see at the real time. Basically, I'm just pressing them and I see how the GPU time is changing. And it gives me a very good information what I need to optimize. And of course, we found quite easily that the bloom and heat shimmer, the post-processing, were taking 1/4 of the frame. So the optimizations there were to go for much lower, to rewrite everything in low precision, because those shaders originally were coming from the desktop shaders, and there were no precision. So after So after we went through the precision, and actually there's one trick. You can lower precision on everything except you don't do that on the texture coordinates. Because if you lower the texture coordinate precision, the GPU will have to convert them back and forth. So one thing was to use the lowest possible precision except on the text coordinates. Then the next thing was to combine bloom and heat into one effect. Because previously it would be, well, let's do bloom first, and then I'm going to do, on that result, let's apply heat. Instead, we could combine them easily into one shader. So instead of 2 passes, it would do 1 pass. And that saved 10 milliseconds per frame, which is quite a lot. The next thing was this burning walls. You can see the walls burning in the background? Yeah. So that was very expensive shader on the walls. It was using like 6 or 8 textures, I don't remember, and quite a lot of ALU instructions and stuff like that. So when I started to optimize that, it was as well, try to reduce the precision. But it was kind of hard in some cases. Actually, that shader was written more or less by the artists. So they just experimented, it looks good enough for them. And so there were quite a lot of room for optimizations afterwards. So the first thing was to try to reduce the precision. In some cases, because it's kind of complicated shader, it was not possible to reduce the precision. So instead, I tried to move as much of that calculations into the vertex instead of doing the high precision calculations in a pixel shader. So quality in some cases reduced a little bit, but you wouldn't notice. So if you cannot reduce the precision, at least try to move that into a vertex shader. The second thing was to refactor a swizzles, because if you're using the swizzling with the low precision, it's very slow. And then using this unpronounceable shader compiler from PowerVR helped to improve, to really to iterate much faster. So I would just feed that shader and see more or less the cycles approximately. So after those walls went 8 milliseconds. So it gives you rough estimation how much you can expect from your expensive shader, that you can make it 8 milliseconds faster, and your post-processing can be 10 milliseconds faster on the iPad 2. The next thing was, because we knew that the scene splits just reducing 10% of the vertices on the characters and stuff like that, we got rid of the scene splits, and then that got us 3 more milliseconds. Optimizing particles, the first thing is just to try to use simplest possible shader. As simple you can get. For instance, usually artists will have a shader where it has for the particle, the texture sampling texture and then multiplying it with some tint color. So just move that tint color, just put that into the texture instead. And for instance, on the shadow gun, that's something else. For lots of the alpha blended surface, in some cases, whether for the lights and maybe for some particles, you can try to add a little bit more vertices instead, but do not sample texture at all, but procedurally calculate the look. And in some cases, it actually works. Not in all cases. But you would, in some cases, you would have to add quite a lot of the vertices to do that. But you can try experiment with that. For instance, if you want some particle which looks like a star, it's pretty easy to do almost procedurally. And then reducing the amount of particles. So our technical artist just went and just tried to reduce as much as possible while retaining more or less the same performance. So all of that combined saved us 25 milliseconds, which gave us more room to add MSAA and anisotropy. We can kill performance if we want. So that's it.
Is that me again?
Yes.
Yeah. I guess this is pretty much like almost repeating the same information. For example, if we profile some of the built-in Unity post-processing effects, like if you take something simple like sepia tone, which makes everything brown, that costs like 3.6 milliseconds on iPad 2. Something like bloom costs like a bit more, color correction yet a bit more, like some noise and scratches and whatever costs not so much. But I mean, all of them, if you like try to put like 4 of these effects, I mean, you're pretty much like end up with like 20 milliseconds of stuff. So that's quite a lot. What Unity makes it very easy to do is to add multiple of these effects onto your camera, which is very easy, but then that's not very optimal. And on desktop machines, you usually don't really notice that much, but on a mobile device where the bandwidth is very, very limited, that's kind of noticeable. So if, for example, if we take like bloom, color correction, and noise, and put all 3 of them together, sort of onto a camera, we get like 13 milliseconds on iPad 2. Now, if we actually combine all these into like one super image effect that does color correction and noise in the same shader as the final bloom pass, then that like saves, well, not that much, but it saves like almost 2 milliseconds on iPad 2. So then if you go to like mobile specific, like PowerVR optimization, you, instead of packing 2 texture coordinates into one interpolator, you use 2 interpolators instead. That saves, again, over 1 millisecond. Then you can cheat a bit, like this noise image effect in Unity that actually has a noise texture and a little sort of texture for like little scratches, but then I look at it and I almost never notice the scratches, so I just remove the texture, and again, that saves a bit. So these kind of quite simple optimizations of like combining image effects together, removing stuff that's not really critical, like in this particular case can shave like 1/3 of the total cost. And that takes like, I don't know, like 1 hour to do or something. So yeah, another case study I had is like I wanted to take sort of the most complex shader I could imagine for mobile. That's not really practical, but I wanted to see how fast can I sort of, how much can I optimize that while it still does the same thing. So I took like a FXAA image effect, which is like anti-aliasing from, I think it's from NVIDIA. And the current state of FXAA is that it takes like 1 millisecond on Xbox 360 and 1 millisecond on PlayStation 3. So I initially I took like the old FXAA 2 version, and so it takes like 1 millisecond on the console. It takes 32 milliseconds on iPad 2. So that's like just nothing in your scene, just that image effect. It's already like only 30 frames per second. So like if you have this complex shader, you want to optimize this. Again, you can try using this PowerVR tool, but then what usually happens is that as the shader is sort of not a trivial one, that tool likes to crash a bit. So when it does, you can try tweaking the shader a bit more, and then sometimes the crash goes away and sometimes it doesn't. So this is probably illustration of like these rules of thumb but not always applying. So I take that initial shader. The common knowledge is like make all stuff that can be in low precision, make that low precision, and that's like twice as low. And like why? No idea. Another thing I like, I look at the generated shader at the end of it. It looks like a complex sort of dynamic branch with like if something then something. I try to kind of use a lerp or something to get rid of that if, but then again it's slower. Why? No idea again, because like this at that point this shader tool from PowerVR, which tells how many cycles for each line of the shader, it was crashing on the shader, so there was no information of like why the so pretty much like the only thing I could make it to do faster is, again, use more varings instead of less varings, which is very much Power VR specific optimization. So that saves like 3 milliseconds, which is still like unusably slow, but a bit better. And then I try to reapply the same sort of, I'll try to use lower precision, but not for everything, but only to some of the variables in the shader. And that's kind of hard to guess to which ones I need to do this, but after like zillion of iterations, I kind of ended up with like 28 milliseconds. So that's like, so in this particular case, I could only get from 32 milliseconds to 28 milliseconds, which saves 4 milliseconds, but that's like nowhere near being usable. Then I took the latest FXAE version, which was a bit more optimized for consoles. So initially, it was already much faster than the previous version iPad, only 22 milliseconds. And again, pretty much the same optimizations I try to apply. Again, just trying to, yeah? 5 minutes, okay. Again, just trying to sort of blindly make everything low precision made it slightly slower. So again, that's kind of, in the simpler shaders, in simple shaders that most often works, but as the shader gets more and more complex, then it gets really not intuitive. So yeah, what in the end, after like, I don't know, 50 iterations or something, what I could get it down to was like 12 milliseconds, which is like almost twice as fast, which is quite good. So 12 milliseconds for anti-aliasing is still like a lot. So like by comparison on that particular scene, the real actual anti-aliasing, the GPU anti-aliasing was only taking like 2.5 milliseconds. But if iPad releases like, I don't know, iPhone 5 next week with magically faster GPU, then that could be usable. So, well, that's it. Do we have any questions?
In 4 minutes.
4 minutes. Oh, come on.
Where did you find the scene split is around? Was it a vertex count, triangle count?
Vertex count.
Vertex. But actually, it's a little bit more complicated. It's vertex count multiplied by number of interpolators. So the number of interpolators you are passing into your shaders from between the vertex and pixel shaders. So that's it has to store this information after it went through the vertex shader. Then it has to. So it's vertex shader multiplied by interpol.
My question is, what platforms is it? Are all platforms taking fixed function and essentially making a shader in the background on mobile?
Yes.
Yep.
Okay. So there's no point in
No.
using fixed function.
No, unless you think it's easier for you to write in fixed function. Yes.
So if, for example, your shader modifies texture coordinates, you will lose that prefix, right?
Yes, of course.
How does it detect that? Is it automatic or
Yep.
Yes.
you don't have to specify
No.
static shader?
No. It just at some point it figures it out. So it's actually for instance for post processing. Usually we do in a pixel we do plus something. Yeah. So it's much better to do that in the vertex shader to offset them first. Yes, there was.
The substance, did you ever try using substance textures, single textures? How would that affect
I don't know how much I can talk about that at the moment, but yes, we tried it. And on the Tegra 3, there will be, for instance, the Shadow Gun will come out with some substance in the future. So in case of, for instance, on something like Tegra, it makes quite a lot of sense where you can, quite a lot of CPU, you can generate your texture, you would generate those textures on the CPU, and your shaders would be much simpler on the GPU. So it makes sense there. And it's probably coming quite soon.
but it's not shipping in Unity yet, and no promises.
Yeah.
Yeah.
Yes, it seems like the Tegra is kind of the odd man out in the group. Like it acts like a desktop GPU.
It is.
And like Unity thinks it's a mini GPU. Is there anything Unity's doing to kind of optimize?
Well, I mean, there's not so much you can do. I mean, Tegra is the GPU, and that's the way it works. And I mean, what else you can do? I mean, sort of, we saw the geometry front to back, as Ronaldo said, like in Shadowgun, they make sure that the character is rendered first before anything else. And there are these things you can do, but I mean, beyond that, there's no magic switch we could do to make it like 3 times faster.
So the one thing we do is we support the DXT5. So if you can build specific build for Tegras or for Qualcomm, like it's not Tegra specific, but when you build something, there is now in the build window, when you select the target, and then there is a small drop-down box, which will convert textures to a specific format, which in case of the Tegra, it will be DXT5, and it will improve performance if you have a lot of alpha blending, basically. Reduce the memory footprint and improve performance. But that's about it sorting and that.
Yes.
So is there any plans on introducing an extended fallback system in the shaders, so you can not just fall back on capability, but fallbacks on GPU? So you can embed different GPUs shaders into one shader?
We can do that with load qualities.
I mean, you can do that with some scripts, right? I mean, shaders can have LOD in them, and then you can switch to like different LOD. But I mean, I wouldn't want to hard code specific GPU models in there because I mean they change each year. Like, I mean, if you do a game that's like kind of picks one or another shader based on whether it's Tegra 2, what do you do when Tegra 3 comes out? Do you rebuild your game? Yeah, but I mean, like, I don't know, most of stuff we've seen, the people don't go like that deep in terms of like writing specific shaders for PowerVR versus Tegra, even though they could do that. But I mean, then most of the stuff is not in the shaders. They try to kind of sort the geometry or do. You could do that, but
Yeah. Significant changes when you were changing.
yeah.
Right. Most people don't even do that. Most people don't even know how to profile that anyway.
Well, I mean, it's like
But you're trying to show us how to do that.
right.
Yeah.
Right. Well, I mean, it's probably a good thing that right now the leading platform where you can earn money is iOS, and that has SGX everywhere. So that's the first platform you optimize for, and then on all the Androids, some of them already have SGX anyway. And on all the Androids, you're not earning money anyway, so why bother?
But if talking seriously, you can do that already. You just need to write a little bit of the scripts, and I think it's yeah. You don't need to swap shaders. You don't need to swap shaders because there is a quality LOD on the shader, so you can just set per shader like LOD what quality you want to. You can.
We should finish.
Yeah. Sorry.
Okay. Well, thanks.